Hello everyone, welcome to Vectorly. Today we are going to solve a few more problems from center of mass and collisions. Most students think center of mass is just formulas, but in today's four Pathfinder problems, COM becomes a storyteller. It predicts who moves, who stops, and who flies off it unexpectedly. And when collisions enter the picture, momentum secretly decides everything, long before the bodies touch. Okay, let's read the question number one. Two identical small balls, A and B, each of mass m, connected by a light inextensible cord of length L, are placed on a frictionless horizontal floor. With what velocity u must the ball B be projected vertically upward so that the ball A leaves the floor? Acceleration of free fall is g. So A and B are both balls connected by a light inextensible cord of length L. Now what are we doing is we are giving a vertical velocity u to the ball B. Okay. First, if you think this scenario, what people make mistake is they will just imagine two balls and they will imagine they are pulling this ball B with a force, which is a variable force, such a way that B moves with a constant velocity u. In that case, what people think is it will move in the line vertical to B. That is this situation. But what happens is in order to move this vertical to B, yeah, you need to apply some force in the sidewards in the horizontal direction too. But in this case, you are not applying any forces. So this situation will be like this. Let me explain why. Here comes the concept of center of mass. So initial velocity of center of mass is nothing but u by 2 into j cap because mu by m plus m. Now acceleration of center of mass is nothing but minus g into j cap. Correct? So there is no component of velocity in horizontal direction as well as acceleration in horizontal direction. So on the whole, center of mass will only move in the vertical line. Correct? It will not move in any of the horizontal direction. So the center of mass will remain in the same vertical line in all the positions. This is one position. And if we move, initially we are giving a velocity u upwards. At some particular point, it has some velocity v. At that point, also COM will be at the same position. Okay, this is the first thing we have to think about this question. Okay, now what happens is, but this body is moving in this direction, right? Anyway, this is moving in this direction due to the string. So at last, this will have a velocity v. In order to compensate that, the velocity of center of mass should be 0, right, in horizontal direction. So we get v over here as both are of equal masses. Now, if you see this properly, throughout the journey, the thread is fixed. So with respect to A, ball B is undergoing a circular motion kind of thing, right? So this is nothing but L. So with respect to A, if I speak, I'm considering A as a point and ball B, if I take relative velocity, it will be 2v and distance is L. Now there comes the tension T will be acting as well as weight mg will be acting down. Okay. Now, if you see the question, what they have given is so that the ball A leaves the floor. Correct. When ball A leaves the floor, the tension over here should be equal to the weight of the ball A. So T is also mg. So total 2 mg force is nothing but the centripetal force. Correct. So it is m into v square, 4v square by r. So what we get is v square is nothing but, if you cancel stuff, gl by 2. This is the first thing. Now they're asking the value of u. So let's conserve our energies. Let's conserve the energy of the center of mass or the system. Okay, the system consisting of A, B, and the thread. Initially, the only energy is the kinetic energy, half m u square. Finally, what happens is both have some value of kinetic energy, that is twice of half m v square. Okay, plus, and ball B has some sort of potential energy in it. So which is mg into L. So half m u square is nothing but m into v square, which is mgl by 2 plus mgl. So what I get is u square is nothing but, sorry, mu square by 2 is nothing but 3 by 2 mgl. And if I cancel, u square is 3gl and u is nothing but root over 3gl. Now you may ask two questions. Why am I assuming that at the highest point of ball B, when the ball B reaches the highest point, ball A will get released? Why can't it go up at some particular position before the vertical height? Correct. In that case, they have to think about it. We are considering the minimum case over here because in the minimum case we are speaking. So the velocity u greater than root 3gl, for any velocity u greater than root 3gl, the ball A will leave the ground. Question number 2. In the setup shown, the block B can slide on a vertical guide rigidly fixed to the wedge C. Okay. Mass of the block A, the wedge C, and block B are m, 2m, and 3m. And cosine of angle of inclination theta of the inclined face of the wedge with the horizontal is 2 by 3. The pulley and the thread are ideal and there is no friction between any of the surfaces in contact. The block B is released from a height 27 cm above the floor. Find displacement of the wedge when block B touches the floor. So, this is the basic center of mass question. Okay, the only thing you have to see is the only force experienced in the center of mass of the system. Let's suppose the initial coordinates of center of mass system is something. Okay, and the final coordinate is something. If you see, the only force acting here is the gravity, which is in downward direction. So overall, the center of mass of the system can only move in y direction, not in x direction. Correct? So the initial center of mass of the system in x direction is the final one too. So initial x coordinate of center of mass of system x com is nothing but, let's suppose, mx1 plus 2mx2 plus 3mx3 whole divided by 6m. Okay, and the final is nothing but x dash of com. So in the final, what is happening is the mass m, which is block A, is moving up the incline and block B is moving down. Okay, so what happens is the block, if we are considering with respect to C and our frame is fixed with respect to C, so what happens is the block B is going down, so x coordinate of block B won't change and block C is also not changing, that is wedge C is also not changing, and A is going right. Okay, if A is going right, the center of mass of the system with respect to C will go right, so the C should move left. Correct? So let's assume C is moving left with x units. Okay, so B will also move x units and A is in contact with C, so it will also move x units, and A is moving some value of units. Let's suppose it is xa. Okay, in this direction. So if you see, B is coming 21 centimeter down, so A should travel 27 centimeters along the incline. So if you see, the cosine is nothing but, cos is nothing but 2 by 3. Let's exactly speaking, its cos theta is nothing but 2 by 3. So for if it is traveling 27 centimeters in this direction, it should travel some xa, right? So XA by 27 is nothing but the cos theta. If you see, XA is in this part and 27 is in this part. So the cos theta is nothing but 2 by 3. So XA is nothing but 18 centimeters. Now I'm going to apply a logic. Which will be greater, XA or X? So the logic over here is, if in a center of mass of a system, let's suppose I have a small body of mass M and a big body of capital M, and the center of mass is over here, and the center of mass remains in the same position. If small m goes a distance L and capital M moves a distance capital L, in order to maintain the center of mass in the same position, and small m is of smaller mass compared to capital M, the logic over here is small l will be greater than capital L. Correct. Because at the end of the thing, we have to make the product should be equal. Correct. So in order to make this, the small l will be greater than capital L. So when we compare, this is 3m mass, this is 2m mass. So only a mass of m is going right. So XA should be greater than X. Okay. So the displacement of A is, what happens is m, initially it is there x1, okay, and it is moving right. So plus XA minus X plus 2m into x2 minus x plus 3m into x3 minus x whole divided by 6m. So x dash of COM is nothing but x COM plus m times of XA is nothing but 18 minus x plus, so overall over here I'm going to put negative, and in the negative sign I'm going to put x minus 18 plus 2mx plus 3mx whole divided by 6m. Now if you see, these both x dash, the final exponent and the initial exponent, both are same. So this is supposed to be 0. So m into x minus plus 5mx is 0. So 6mx minus 18m is nothing but 0. So you get x is equal to 3, which is 3 centimeter. As we are units we are speaking is in centimeter. So the main concept here is simply the conservation of the center of mass coordinates. But the thing is, XA is greater than X is the main important logic you have to encounter. Uh, Let me give a tip. Try solving by considering X is greater than XA, and you will figure out why I'm not using that assumption. Question number 3. A thin plate A of mass M is affixed on the upper end of a spring, lower end of which is affixed on the ground. In equilibrium, the spring is compressed by an amount x naught. Another thin plate B of mass 2m dropped from a height 3x naught above the plate A hits the plate A, moves downward together with plate A, and after reaching a lowest point, both the plates rebound upwards. What maximum height above the initial position of the plate A will plate B rise? So here the plate B's mass is 2m and plate A's mass is m. Initially the thing is fixed, okay? This is compressed by x naught. So I have represent this in a beautiful diagram over here. So this is the natural length, that is relaxed height of the spring. Now what happens after placing A and fixing it, it goes down a distance of x naught. So from this what you can conclude is, let's assume the spring constant as k. Okay, so kx naught is nothing but mg, because A is at rest now, is in equilibrium. Okay, and we are putting B, which is 3x naught from A, so 2x naught from the relaxed height, correct? Now what happens is, B will come. Let's continue the story. First, if we drop it, B will come and hit the plate A with what velocity? We have to find that. Let's use the conservation of energy for B. Let's keep this as the base, as a reference line for potential energy. From this, the initial energy of B is nothing but the potential energy, which is 2m mass of B, G into H is nothing but 3x naught. Okay, which is, what is the kinetic energy over here is, because potential energy is 0. So what you get is V is nothing but under root 6 G x naught. Okay, so the velocity with which B is going to hit the plate A is nothing but root 6G x naught. So this is just before collision. And after the collision, they both combine and become a body of mass 3m. Okay, so what happens is here occurs inelastic collision. So between 2 and 3, energy is not conserved. Okay, so let's find the final velocity. Initial, so in case of inelastic collision, because why it is inelastic collision? Because they have mentioned that above plate A hits the plate A and move downwards together with plate A. So it is an inelastic collision. So the initial momentum is 2m into under root 6g x naught. And finally, the mass 3m is moves with the velocity v dash. Okay, that is v dash is the combined velocity. So v dash is nothing but 2 by 3 into under root 6g x naught. So this, if this is at this point it has a velocity v, and now this velocity is become v dash. After this, what happens is this whole system will move to the lowermost point, and what happens at the lowermost point, the spring will be more compressed, right? So it will exert a more upward force than the weight, so it will push upwards. So till pushing upwards, the spring force will be along the direction of motion. When the spring reaches the relaxed height, that is from the initial height x naught, when the spring moves, what happens is it will start pulling back A, but A, B have no connection, right? So B will keep moving upwards, but A will face an acceleration downwards much greater than B. Okay, at this point, A and B will get separated, and B will reach the topmost point after this. That is the case 5. Okay, so now what are we going to do is from 3, 4, 5, in between the parts 3, 4, 5, the energy is conserved. Okay, between 2 and 3, the energy is not conserved because of inelastic collision. But in 3 and 4, 5, the energy is conserved. So let's write the energy equation. Initially at 3, what happens is we have the, let's keep the potential energy reference as this line. Okay, that is x naught below the relaxed height. So initially the only energy it has is potential energy. The first potential energy is the spring potential energy, which is half k x naught square, plus the potential energy of the bodies, which is 0. Sorry, it has kinetic energy too, right? So which is half, so mass 3m has a velocity of v dash square. This is the initial energy, right? So if I expand it, what I get is half k x naught square plus half 3m into 4 by 9 into 6g x naught. So half k x naught square plus 2, 2 gets cancelled, 4g x naught, which is nothing but, what is 4g x naught over here? So multiply x naught here. So k x naught square is nothing but mg x naught square. Sorry, mg x naught. X naught into m. Okay. Now this thing is nothing but g x naught m is nothing but k x naught square. So we will get 9 by 2 k x naught square as the initial energy. And what about the final energy? The final energy is nothing but, in this case, when B reaches the topmost position. Okay. When B reaches the topmost position, there is a issue in conserving energy between 3 and 5. What is that issue in? When B reaches the topmost position, we don't know the exact height of A, okay, and velocity of A in order to equate the energies. So we can't directly find using this. So let's conserve energy between 3 and 4 and find the velocity of B at the topmost position. And then we can find out the height reached. So what happens is this is the energy in third case. Now let's calculate the energy in fourth case. In energy in fourth case is nothing but both have some velocity, right? So and the spring is relaxed. Okay, both have some potential energy too. So the potential energy is 3 mg into x naught. Correct. Because we are keeping this as a reference line, so it is x naught above. So 3 mg into x naught, and both have some kinetic energy. So half into 3m into v square. Okay, let's consider v2 square, which is nothing but 9 by 2 k x naught square. So 3 mg x naught plus 3m by 2 v2 square is nothing but kx naught square is something but mg x naught. So we get mv2 square is nothing but mg x naught, and v2 is nothing but under root 2g x naught. Sorry, under root g x naught. Okay, but what happens is if at this point the velocity here is v2. Now from the height, maximum height reached by the plate 2b is h max is nothing but v square by 2g. So just v2 square by 2g. So gx naught by 2g. So it reaches x naught by 2. So from this line, the plate B reaches x naught by 2. But what are they asking? What maximum height above the initial position of the plate A will plate B rise? So the initial position is x naught below. The initial position of plate A is x naught below. And the final position, the maximum height reached by B is x naught above the line. So the final height above the initial position of A is x naught plus x naught by 2, which is 3x naught by 2. So this is our final answer. So the thing we are going to conclude from this question is we have to consider all the steps occurring in the particular question. We have to analyze each and every step because we can't. Anyway, we are going to conserve energy between 3 and 4. We can't directly conserve energy between 1 and 4 directly because there is an involvement of inelastic collision over here. Okay. Question number 4. A small disk sliding on a frictionless horizontal floor with an unknown velocity collides head on with another identical disk kept at rest on the floor. If during a time interval tau, the first and the second disks cover distance s1 and s2 respectively, find possible values of initial velocity u of the first disk and the initial distance L between the disks. Okay. Now what happens is, let's assume this situation. Let this be the disk 1 which is moving with the velocity u. Initially the disk 2 is placed over here and the distance between them is L. Okay. After collision what happens is finally the disk 1 goes some distance over here and disk 2 goes a distance over here. So the overall distance covered by disk 1 in time tau is s1 and disk 2 is nothing but s2, and let the final distance between the disks be x. Okay. Now, just after collision, disk 1 gets a velocity v1 and disk 2 gets a velocity v2. The time taken for the collision, let's assume as small t. Okay. Now, the total distance covered first, s1. Let's write the equation for s1. So s1 is nothing but how are you going to cover s1? First time, what are we going to do is L can be written as u into t. Okay, let's write this separately. So L is nothing but u into t. We are having this relation over here. So S1 is ut, that is L, plus the remaining part we are going to travel. So this remaining part is nothing but tau minus t, the remaining time, into v1. Correct? What about s2? So in s2, what are we going to do is, with v2 velocity, we are going to travel for tau minus t time. Okay. Now we want u. Correct? So u is nothing but s1 minus of tau minus t into v1. Okay. And the we have another relation between v1 and v2. Let's explore. First, the initial momentum mu is nothing but the final momentum mv1 plus mv2. Correct? We are applying the conservation of momentum. Okay, so u is nothing but v1 plus v2. So let's not write this way. Okay, let's write it in different way. Let's first express v1. V1 is nothing but s1 minus ut by tau minus t. Okay, v2 is nothing but s2 by tau minus t. So what are we going to do is write u as v1 plus v2. So which is s1 plus s2 minus ut by tau minus t. So if you see u into tau minus t is nothing but s1 plus s2 minus ut, and L is equal to ut, which gives you t is nothing but L by u. Okay, so u tau minus ut is equal to s1 plus s2 minus ut. So directly you can see that u is nothing but s1 plus s2 by tau. So you got the relation for initial velocity u. Now let's find the relation for the initial distance L between the disks. Okay, so what thing we can conclude is, anyways, S2 plus L is nothing but S1 plus X. Correct? S2 plus L is nothing but S1 plus X. So L is nothing but S1 minus S2 plus X. Okay, let's analyze. Anyways, this collision may be the extreme cases. Let's consider elastic one or inelastic. As both are of equal masses, if they are in elastic one, what happens? S1 will be equal to L. In case of elastic, S1 will be equal to L. Okay. In case of inelastic, what happens is X would be 0 because they both travel together after the collision. So, okay. In case of elastic collision, L will be S1. So, in case of inelastic collision, L will be S1 minus S2. Okay. So, the maximum value of L max is nothing but S1, and L min is nothing but S1 minus S2. So L goes from S1 minus S2 to S1. This is what the condition that is going to be applied on L. Okay. So this kind of a very different question, because sometimes you don't even understand what are they trying to ask. Okay. You have to figure out things, and we have to assume some things like that we are going to start the clock by just before the velocity is u and the distance between the disks is L and all. I hope this all four questions will be interesting. Try solving this. If you have any doubts, just comment it. Thank you.